Okay, so let's continue where we stopped. We consider the rejection region. Let's consider the acceptance region now. Okay, so all our sample variables, let's say inside of the acceptance region case, and in that case we assume that the simple likelihood ratio under the null hypothesis and under the alternative should be greater than or equal to k1, which is unknown right now, and then we can write it like the previous case as greater than or equal to k1, writing the definitions. Then we obtain that, okay, so we have 1 minus alpha, which equals to n equals 1 from infinity, the acceptance region theta 0. Okay, so greater than or equal to, so k1 times summation n equals 1 to infinity, the acceptance region under the alternative, and this is the definition of beta. So from here we have the relationship between k1 and alpha and beta. This is k1. Okay, so after deriving that, what we can do, okay, so we have an inequality here, and in the previous case we have an inequality. So how can we define k0 and k1? So then we assume that we have some values actually, so equality values, so other than the inequalities like less than or equal to or greater than or equal to. So we let our k0 equals to alpha a over 1 minus beta a, and k1 equals to 1 minus alpha a over beta a. Okay, so using these inequalities, replacing alpha by alpha a and beta by beta a, certain alpha and beta values should satisfy these inequalities. Okay, so using that, so we can say that from here, so let's focus on the first part first. 1 minus beta should be less than or equal to k0. What is k0? We define it as alpha a over 1 minus beta a. Right? For any alpha and beta can satisfy this. And from here, we can say that our alpha should be less than or equal to 1 minus beta k0. Okay? And since this quantity is between 0 and 1, we can define that our alpha should be less than or equal to k sub 0. Okay, so this means that then it is alpha should be less than alpha a over 1 minus beta a, which is k0. Okay, and yeah, we have this, and equality observed if and only if our beta value is 0. Okay, and let's focus on the k1 part. So we have 1 minus alpha over beta greater than or equal to k1, and we define it as 1 minus alpha a over beta a. Okay, so from here we can write it this way: beta over 1 minus alpha less than or equal to 1 over k1. And then this means that beta should be less than 1 over k1, 1 minus alpha. Again, this 1 minus alpha term is a positive value between 0 and 1, if alpha is a probability. Then we can write it as beta should be less than or equal to 1 over k1, which is beta a over 1 minus alpha a. Okay, and for certain alpha and beta values, this should be satisfied, and equality observed if and only if alpha equals to 0. Okay, and this alpha value is a small number. We fix it like 5%, and from the above case also beta is a small number. Usually we set it like 5%, 10%, like type 1 error probability. So this means that basically combining all these things, we have 1 minus alpha times 1 minus beta A plus beta times 1 minus beta. What did I write? So there should be an equality. Sorry. There should be an inequality times. Okay, so I made a mistake here. So let's erase all these. Okay, so this should be less than or equal to 1 minus beta alpha A. Okay, and then from the second part we have beta 1 minus alpha A should be less than or equal to 1 minus alpha beta A. We have these inequalities. Okay, then when we add all sides, okay, so add them. So what we have here is 1 minus alpha times 1 minus beta A plus 1 minus alpha A less than or equal to alpha A plus beta A. And what we have here is okay, minus alpha A beta minus alpha beta A. Okay, and from here when we open up the parentheses here, we have alpha minus alpha beta A from here, and beta minus alpha A beta here, and here we have alpha times beta A. This term and this term cancels out. We have minus alpha A beta minus alpha A beta here, so this means that alpha plus beta should be less than or equal to alpha plus beta A. So these are actually greater than the alpha and beta values that we set. Okay, and in most cases basically we set these alpha and beta values equal to the alpha A alpha beta values, and we will use this actually. Okay, so they are exactly not equal to each other, alpha A and beta A, and it was observed in many applications that alpha is close to alpha sub A, and then beta is close to b sub A. So if we set it like that, then we can predefine our alpha and beta at the beginning, instead of using the true alpha A and alpha B value, beta A values. We can use the pre-specified alpha and beta values that we set at the beginning of the test. Okay, so we are approximating alpha A by alpha and beta A by beta. Then it will be very easy to define our K0 and K1 values, because remember we set our K0 like that and K1 like that. Instead of alpha A and beta A, we can replace them by the pre-specified alpha and beta values. Okay, so suppose these are the most used ones. Suppose we want our alpha is close to 0.05, and let's say our beta is close to 0.0, not 0.010, okay, 0.10. Then we can take alpha A as 0.05 and beta A as 0.10, and using those we can obtain K0 as, what was the K0 formula? Let's go. So alpha A over 1 minus beta A. Oops, sorry. Okay. Alpha A minus 1 over beta A. If you remember one of them, the other one is the reverse kind of, 1 minus alpha A over beta A. So 0.05 minus 1.010, and we obtain 1 over 18. And similarly, K1 is 1 minus alpha A over beta A. So 1 minus 0.05 over 0.10, we obtain 9.5. Okay, so after defining K0 and K1 values, we don't have any unknown terms. Then we can define our rejection region based on these values. Okay, so this value is close to 0.056 actually. Okay. Uh, okay, then our alpha value should be less than 1 over 18, which is 0.056, and our beta value is less than 1 over k1, it's equal to, which is 1 over 9.5, 0.105, this is 5. Okay, so when we draw a picture of alpha and beta error probabilities, so we will have something like that. So these are 0.15 and 0.15, where alpha and beta equals 0.15 here. Okay, because alpha and beta, when we add them up for the given values, we observe that. So this point will be 0.105 and this point will be 0.56 approximately. This is the given alpha and beta values. So our rejection region basically here and here, but if we give it in this area, so we will have this area actually in terms of type 1 and type 2 error. So this will give us the total error that we have. Okay, then for the UMPT case, suppose we have a monotone likelihood ratio y, and ln depends on the sample only through y, and it is, and let's say increasing. You know how to deal with the decreasing case, just use minus y of y for our regular condition, whatever the hypothesis is we are using this, remember. Okay, sorry. So if this is the case, then let's say we are testing theta 0 and theta less than theta 0. So in this case, our rejection region will be reject A0. Actually, we don't say if here. You can use if, but this is the regular procedure. As soon as ry less than or equal to some c0, equality is important. Okay, don't forget it. If I forget in somewhere, please add in your notes. Y greater than or equal to c sub 1. Okay, here in both acceptance and rejection region we have equalities, and we have an inconclusive result and continue taking samples if y is between c0 and c1. Okay, sorry, c0 here. So when you do the calculations, basically you will ended up with the true condition, so don't worry about that. So your calculations give you the correct region for the continued case. Okay, so let's focus on some examples here. Okay, let's up. Let me see. Okay, so we have a Bernoulli case.